You know, everything in the universe, from the fan wearing in your computer to galaxies hurtling through deep space, nothing is ever truly standing still. So today, we're going to break down the fundamental rules of motion, the physics that explains, well, everything that moves.
So, let me start by asking you a question. Are you sitting still right now? I mean, you probably think the answer is yes, right? But the truth is, it's a little more complicated and honestly, a lot more interesting than that.
You see, the answer to that question completely depends on your perspective. In the world of physics, figuring out if something's moving or standing still all boils down to one single crucial idea: your reference point.
So, what is a reference point? Well, think of it as your anchor, your starting line. If I say a school is 2 kilometers north of the train station, that train station is our reference point. It's our origin. Without it, saying 2 kilometers north doesn't really mean anything, does it?
And this is exactly what scientists mean when they say all motion is relative. You know this from experience. If you're on a moving bus, it feels like the trees outside are zooming backward. But for someone standing on the sidewalk, it's obviously the bus that's moving. And here's the thing. Both of you are right. You're just using different reference points.
Okay, so to really describe motion like a pro, we're going to need a toolkit of concepts. Let's start with two of the big ones: the actual path you take and, well, the shortcut.
Let's try this out. Imagine you're starting a trip at what we'll call point O. That's your origin. And you just start walking in a straight line. Okay, so you travel a good 60 kilometers and get to point A. But then you have a change of heart, you turn right around and you walk 35 kilometers back, finally stopping at a new spot, point C.
So how far did you actually walk? Easy enough, right? We just add the two parts together, 60 kilometers out plus 35 kilometers back. That gives us a grand total of 95 kilometers. In physics, we call this the distance. It's the total ground you covered.
Okay, but hang on. Here's a totally different question. Forget the long path you took for a second. How far are you, in a straight line, from where you started to where you ended up? What's the direct shortcut?
The answer? Just 25 kilometers. Even though you walked a whopping 95 kilometers, your final position is only 25 kilometers away from your starting point. This measurement, the direct line from start to finish, has a special name. We call it displacement.
So let's lock this in. Distance is the total mileage, every single step. Displacement is just the shortcut from your front door to your final destination. It's why you can run a whole marathon, but if you finish right back where you started, your total displacement is 0. So how does this idea change how we talk about speed?
All right, next up in our motion toolkit, it's not just about how far you go, it's also about how fast you get there. And just like before, there are two different ways to look at it. There's how fast, and then there's how fast, and in what direction.
Let's check out this example. We've got Usha, who's swimming laps in a 90-meter pool. She swims from one end to the other and all the way back. So she covers a total distance of 180 meters, and she does it in exactly 1 minute.
So if we want to find her average speed, it's pretty simple. We take the total distance she traveled and divide it by the time it took. For Usha, that's 180 meters divided by 60 seconds.
Do the math, and you get an average speed of 3 meters per second. Seems simple, right?
But hold on a second. What if I asked you for her average velocity? Now you might think it's the same thing, but get ready for a twist.
And here is the catch. Speed is just a number. It tells you how fast, but velocity is speed with a direction. Now think about Usha. She started at one end of the pool, and she finished at that exact same end. So what was her displacement? 0. And since average velocity is just displacement divided by time, her average velocity is also 0. She was moving like crazy, but because she ended up where she started, her overall velocity was nothing.
Okay, we've covered distance, displacement, speed, and velocity. We're building a pretty good picture here. But what happens when that velocity changes? This brings us to the last major tool in our kit, acceleration.
You already know this feeling. When you hit the gas in a car and get pushed back in your seat, that's acceleration. It's just a measure of how quickly your velocity is changing. And when you hit the brakes, that's acceleration too. It's just negative acceleration, or what we sometimes call deceleration.
Let's look at Rahul on his bike. He starts from a stop and, in 30 seconds, gets up to a speed of 6 meters per second. That gives him a positive acceleration of 0.2 meters per second squared. Now that squared part just means that for every second he pedals, his velocity increases by another 0.2 meters per second. Then he hits the brakes, and his acceleration goes negative as he slows down.
Now this is where it all gets really cool. We can take all these numbers and ideas and turn them into a picture. By using graphs, we can actually tell the story of an object's motion visually.
Check out these two distance time graphs. The one on the left, with that straight, sloping line, that's the story of a nice, steady, constant speed. But the one on the right, the curvy one, oh, that's a different story. That's a story of speeding up, slowing down, maybe getting stuck in traffic. The shape of the line literally tells the story of the trip.
And here's the raw data that might make a graph like that. This is a car's velocity checked every 5 seconds. Do you see the pattern? Every 5 seconds, the velocity goes up by another 2.5 meters per second. That steady, predictable change, that's the signature of uniform acceleration.
And that brings us all the way back to the beginning. Are you sitting still? Well, relative to your chair, yeah, but you're also on a planet that's spinning and hurtling through space. And what's amazing is that with just these few simple tools, displacement, velocity, and acceleration, we can describe both of those journeys. So the next time you see anything move, whether it's a leaf falling or a jet soaring overhead, just remember there's an invisible story being told, a story of perspective, change, and the beautiful rules that govern our entire universe.